Hey, welcome everybody. I have to re-record a few concepts that I covered in class because I forgot to share my screen. So the recording has all blank screen throughout. All right, so it's going to be a quick video because I had to spend some time answering questions in class, which I don't have to now, obviously. So unfortunately, I cannot get back recording for those Q&As, but that's okay. So the concept that I want to cover in this special recording is the type of DRAM arrays that we encounter in practice. So there are two major kinds. One is the folded bitline array. The other one is open bitline array. In the open bitline array, which is more close to our conventional understanding, we have DRAM cells organized in columns and rows, as you see, as we kind of can easily understand. And every column is fed to one sense amplifier. And then this sense amplifier will need a reference separately to sense during read operation. Okay, so every cell in every column will have one common data line or bit line. It could be data line or bit line, whatever you want to call it. Okay, and that's same across all the columns. And the rows are pretty straightforward too, because all the rows will have the same word line as you can imagine. For the folded bitline array, on the other hand, it's a little bit complicated. So the cells in the same column will not always have the same bitline. The odd numbers of cells, like number 1, number 3, and so on, and number 5, number 7, they will all have the same bitline, maybe this one on the left, and the even numbered cells, 2, 4, 6, and so on, they're connected to a different bitline. So the neighboring cells in the same column are connected to different bitlines. One connected to the left bitline, the other one connected to the right bitline. Okay, so keeping that in mind, oh, by the way, when you sense, you provide these two bitlines to one sense amplifier, because one of the bitlines act as reference for the other one. And to understand this better, let's get to more detailed view of the array. This is a open bitline situation here, where you have all these memory cells connected to the same bitline, as you see. So this is one block of the array, and this is another block of the array, and you have the sense amplifiers running in between, for example. So the way we generate the reference for sense amplifier is by using one of the blocks as dummy reference. Okay, so let me explain what that means. So during read operation, we pre-charge the bit line to VDD/2, as you know. So we do that for both sides, for this one and the other side as well. So this line will also be pre-charged to VDD/2. Now imagine you're trying to read this cell. That means the word line will be activated. And if this cell was storing 0, this bit line will discharge. If this cell was storing VDD, this bit line will charge up. So you either have plus or minus delta V added to VDD/2. Okay, so this will either go up or go down from VDD/2. For the other one, all these word lines are deactivated. So there will not be ideally any discharge or charge for this bit line. Okay, so therefore this could stay at VDD/2. The other one changes, and the sense amplifier just senses whether this bit line went up compared to VDD/2 or went down compared to VDD/2. And then it can determine whether the data that we are trying to sense was 0 or VDD. Okay, so that's how you generate reference. And the problem, there is one major problem with this approach. As you see, the reference generation circuit, reference generation block, is physically separate from the cells that you're trying to read. Now, when some sort of noise comes, or you have some sort of aberration, electrical aberration that leads to changes in the voltage, imagine this bitline voltage was VDD/2 plus minus delta V. There could be a noise voltage connected to this as well. But the noise will not affect the reference section equally. The reference was say VDD/2. The noise may not affect the reference at all, okay, because it's physically separate, and chances are low that they will be affected similarly by the same noise source. And that's what leads to challenges. This noise could disrupt your read operation and eventually lead to incorrect reading. But when you read from the folded bitline array, which is here, as you see, the cells that are connected to one bitline, maybe you're trying to read this bitline first. So this cell first will go through changes. Let me start with this one. Let me show you. Say both bitlines could be precharged to VDD/2, and you only activate these row for the cell that you're trying to sense. Maybe you're trying to read this cell, okay? Both bitlines, both neighboring bitlines are precharged, but only word line corresponding to this cell is activated. The other word line corresponding to these cells are not, okay? So they're deactivated. So this bitline will ideally stay at VDD/2 unchanged, but the other bitline, this one, will discharge or charge. So depending on what's being stored, it will either go up or go down in voltage. Okay, so the same argument. So this sense amplifier can now figure out whether the bitline that you're trying to sense went up or went down, and depending on that, it could tell whether it was storing 0 or 1. Now, in terms of noise, since these are physically close to each other, they're kind of located within the same block. If a noise source comes, it typically affects both bitline the same way. So Vn and Vn. So you have the common noise coming to both inputs of the sense amplifier, and they will be treated as common mode noise and canceled out. So that's the biggest advantage of having a folded bitline array. And what is the bigger disadvantage? Of course, by if you could connect all the cells to the same bitline, you could have saved area. But by going through the folded bitline approach, we are basically wasting a lot of area. For example, when you connect this cell here and don't connect the next cell right away, let me show you here. So you connect this cell to this bitline and don't connect anything here. That means you're wasting area. These are void, for example, right? Even if you see visibly, but in layout, we don't basically do it this way. We practically fold them in. But even so, because of some additional contact that you need to connect them in different bitlines, there will be higher cell area in this type of folded bitline array, and that is the bigger disadvantage. And also, you need a specialized arrangement for the sense amplifier versus the one that you saw here. Basically, the sense amplifiers could be right here as a as a central element, but for the other array structure, it will be more complicated. Okay, so these are the two disadvantages of folded bitline array. But if you need noise immunity, that's a great option for you to have. The next concept that I want to cover is temperature concept compensated self-refresh. As I already discussed, that DRAM arrays require refresh, and we refresh per row. Every row, for example, if you have an array like this, we start refreshing from the first row and we go through all the rows until we are done, and we go back to the first row again. So this is more like a cycle that goes on perpetually, okay? Now, there is a rate of refresh that we have to keep in mind. Do we refresh every microsecond or every millisecond, every 100 microsecond? How frequently should we refresh it, right? For example, you are not reading the DRAM array for a while. Do I keep refreshing at a higher frequency, or should I just reduce my refresh frequency? That's the bigger question. So turns out transistors become leakier at higher temperature. When temperature increases, the off current of the transistor will go up. So that means that the stored data in the DRAM array, so the capacitor, basically the capacitor that we have in the DRAM array, will lose more charges at higher temperature. That means we need to refresh more frequently, okay? But if we keep refreshing unnecessarily, we could keep refreshing frequently unnecessarily at every temperature, but that will spend a lot of energy, of course. So what we do is, at lower temperature, we could reduce the refresh interval, like we could reduce the refresh frequency and increase the refresh interval. But for higher temperature, we have to increase the frequency, and that will become more energy hungry, as you can tell. How do you determine what's the temperature now? We always have on-chip thermal sensors spread across the hardware. They spread across the chip in the logic block as well as the memory block, and that tells us the temperature in different localities. And based on those temperature reading, we could change or dynamically change the refresh frequency of DRAM, and this is necessary to save power. Another interesting concept to further save power would be to use partial refresh or deep power mode. And here is what I mean by that. Imagine when you are accessing the DRAM array for a computationally extensive task, like maybe you're gaming. That means you need all the memories that your DRAM can offer, all the blocks that your DRAM can offer. So sure, you keep refreshing all the banks, bank 0 to bank 3 or whatever, right? As many banks you have. So you keep refreshing all of them regularly so that they're usable all the time. But imagine you are not really doing such a computationally extensive work. Maybe you're just texting, right? That means you don't need that much memory. So in that case, you just separate out a few banks that you might need for your application and put the other banks into more like a power down mode, meaning these blocks or these banks will not be refreshed. The other ones, the ones that you see here grayed out, will be refreshed periodically. That saves a lot of energy in terms of not refreshing the banks. Of course, there are many other banks that you may not need to refresh, and you have to co-design it with the software and make sure that you allocate enough memory for your program to execute properly. On the other hand, imagine you are not using your system for a while, then there is no need for example, you're not using your cell phone for a while, it's just sitting there. Why don't we go to deeper power down mode and not refresh any of the banks? Remember, if you don't refresh a bank for a period of time, the data in there will be invalid. You have to basically reinitialize everything, which is fine. If you're not using the DRAM, there is no need to keep the old data. This is basically just junk that you anyways will get rid of during the next cycle. So we can stop refreshing all the banks if necessary in deep power down mode. So all of these techniques are applied in actual hardware to save energy. The other concept that I want to highlight is the concept of 4F square area footprint. So here is what I mean by that. F represents half of the minimum feature size. What does that mean? What is minimum feature size? Minimum feature size is the minimum dimension that you can create. Maybe this is the minimum dimension that you can create at a given technology node of a transistor. And that is determined by our instrument. Can we create a 10 nanometer line? Can we create a 20 nanometer line? What is the minimum that we can create? Okay. So imagine your minimum is 10 nanometer for a technology. That means you can have 20 nanometer, you can have 30 nanometer or 50 nanometer, but you cannot have 11 nanometer. Because how will that one, you can, for example, you cannot have any fractional nanometer compared to this. So for example, you cannot have 9 nanometer, for example. You cannot have 7 nanometer, for example, okay? Because that's simply unachievable. Okay, so keeping that in mind, if is half of minimum feature size, what will be the minimum feature size? That will be 2F. For some reason, industry folks always prefer representing the minimum feature size in this form instead of putting F to be the feature size. Okay, so F is half of the feature size. So 2F is the minimum dimension that you create in a technology. So when you create some sort of pattern in a silicon wafer, the minimum X dimension that you can have is 2F, because 2F is your minimum feature size. And the minimum Y dimension you can have is 2F again, because that's your minimum feature size. So what is the minimum area? The minimum possible area would be 4F square. So if you create a memory cell that has 4F square footprint, that means you have made sure it's optimized to the fullest extent of technology. You cannot have anything less than that. Okay, so we are all running after 4F square cell layout footprint in memory design. Now, getting back to this one, at some point in DRAM architecture, we used to have 6F square cell footprint. Here is why. So you have a transistor, and on top of transistor, you have to create the capacitor. So imagine you create, this is your transistor footprint. If your capacitor, when you try to scale it up, when you obviously want to make a bigger capacitor to store more charge, the capacitor could take more area, and it could be there could be an offset in terms of area, right? If there is an offset, what is the total area? The total area would be something like this, including the capacitor and the transistor. So instead of 4F square, you get more. The area eventually could become 6F square or 8F square or more than that, depending on how much offset you have in the capacitor. So people figured out through intelligent device engineering a way to bring this capacitor completely within the footprint of the transistor, okay? And that's what led to, so if your transistor footprint is this, which is 4f square, if you could put your capacitor completely within the footprint, then your overall DRAM cell area is still 4f square. And that's what we would call a magic combination. So this is a stacked capacitor DRAM where the capacitor stays completely within the transistor footprint. Okay, and quite often people use an interesting transistor technology. Let me show you that one here. It's a vertical transistor, vertical channel transistor. So typically when you look at a transistor structure with a source, drain, and gate like this, the channel is horizontal like this. So electrons can flow from, say, source to drain. Okay, so it's horizontal. But what if I create a transistor? This is essentially a transistor, as you see here. The source or drain, whatever you want to call, they're interchangeable. Say this is source and this is drain. And inside you have a channel. So the channels are here, circular, if you think about it this way. Okay. So the channels are vertical. This is how the electrons are flowing. So this is vertical channel transistor, and they're very exciting in terms of scaling the dimension of the transistor in itself. So after you have this vertical channel transistor, on top of it, you can have these cylinders of capacitor. And that's how you could get the best possible integration density for DRAM. Okay, and as you notice here, this dimension could be 2f for one of them, and this dimension could also be 2f. So you have 4f squared cell footprint. And this is a realistic, real image, SEM image of such a transistor, vertical channel transistor. By the way, this is your channel, and you have, say, source and drain, and this is the channel through which the electrons will flow. Okay. All right. One more thing. This blue region that you see here, that's your word line. Word line creates the gate, by the way. This is your gate. Your channel will be wrapped around the cylinders, the gray cylinders. Let me point them out. These are source and drain, and the channel will be around, this circle, basically. So the gate is wrapping all around the transistor. So this is often called as gate all around transistor, GAA transistor. Okay, gate all around transistor. I mean, if I could draw a 3D image of it, it would be something like this. So the red one is your conventional semiconductor, and the green one is basically the gate, which is wrapping all around, and there will be some thickness, of course. So wherever you have the green one overlapping the red one, you'll have a channel. So the channel will be also circular, but inside, between the green zone and the red zone. I hope you can, it's difficult to explain with just 2D drawing, but I hope you get the picture. Okay. We're not getting into the detail of the transistor technology here in this course. We just want to care about the memory, but just wanted to add this, tangential concept to help you understand why people would go through this special transistor to save area, because the conventional bulk MOSFET will take up more area than this vertical transistors. So that's how critical it is to save area for memory design. Okay, that's what brings us to the close of this lecture, and thank you so much for listening.